how many times has it been accelerated?
That I don't remember. Really. No, this is actually we have done. This paper actually gave the first actually this 1 by r cube forces between two spheres in nematics was theoretically experimentally shown by the group of Lubenskis and his co-worker actually. So, okay. But there is a story here. The forces between two embedded particles in nematic was actually first thought by Sriram Ramaswamy in 1996. And in the calculation, he came up that, if I remember the title of this paper, this power law forces between two particles in nematic liquid crystals. He came up that force is always 1 by r to the power 5, which means he was getting stable defect having Saturn-ring type. Okay? He could never imagine that Saturn-ring could slip from the equator and become a point. That is the point he missed. That's what he told me. So this is a rather weak interaction. You can see the 3000 kBt. So when they are far, and then of course this close means somewhere here. And this is also highly anisotropic. In fact, this was really published in rather infamous journal, the impact probably 0.5 or so. But that is what things started actually. Next year, these guys, they discovered that you have actually much more interesting thing. And then later on, I don't know how many good papers are published. Till now, every issue in Science Nature, you will see 1 or 2 papers are actually there and still on these defects. Anyway, so this is highly anisotropic, forces. Now we asked another question. So because nematic has been really studied to a great detail, and so not much scope was there to do something. So we thought, so you have a smectic liquid crystals. So apart from the orientational order, you have a layering of the smectic, a layered structure. If we put foreign particles like this, what happens? Answer is very simple. If you put, they will be thrown out. Means the particles do not go inside this smectic. Simple reason is that if you look at this elastic free energy, you have two terms. These terms, this B is called smectic layer compression modulus. The moment you put a particle, layer tend to get compressed, and since B is quite large, it actually expels the particles. So particles always go outside this smectic toward the surface. Okay, so it was difficult. So that means since B is quite large, so any distortion which is related to the compression of the layers, which costs huge energy, is not permitted. Okay. What is permitted in smectic is that, for example, this kind of splaying of these molecules. That means you have a layer structure which you can bend. This does not cost much energy. In fact, that is gained by this one, which is much lower. That means you can have a splay deformation of the molecules in this layer, means layer can curve like this. But you cannot have a bend deformation of the molecules, which means layer cannot be separated like this, right? Because you are changing the layer spacing as you go in this direction. This costs huge energy. So, sorry? Particle is much bigger than this layer. The typical layer thickness is around, let's say, 20 to 30 angstrom, but particle is few micron size. Okay, right. Now, so what we did that how do we embed such particles in smectic? So we thought we know this particle can be embedded in nematic. So we take a system where we have a nematic to smectic-A phase transitions. Okay, and then you cool. Therefore, once it is inside the nematic, if you cool down, since the molecules are strongly anchored, they cannot be expelled from the bulk of the smectic liquid crystal. Now we took two liquid crystals, two types of liquid crystal. You can see that it has both isotropic, nematic, and smectic-A phase transitions. So it's a quite low temperature. So you have around 40 to 33 is the nematic, then around 33 to 21 you have smectic phase. So you always start experimenting in the nematic phase and cool down and go across the phase transitions. These are two different types of molecular structure. The difference I will tell you later why we have chosen. The elastic constant, one of this K, in this case, the K33 is much lower than the other one. Okay. And this is a kind of silica particle we used, and you can see a very smooth surface. And since I want the liquid crystal molecules to be anchored in a specific manner, either they are horizontal or they are vertical, we give some sort of surface coating. In short, this is called DMO AP. Means if you give this coating, so what happens? I can make these molecules, perpendicular to the surface, or I can make it planar, depending upon the choice of the, the chemicals. Now, this is the experimental setup. This is basically a optical tweezer, although I am not creating as such any trap or trapping the colloids. This is just to manipulate this particle. I will not go into the detail. Essentially for me, this is a highly focused laser beam which will help me to manipulate this particle wherever I want. And there is a acoustic deflector which actually can create thousands of strap or beam for manipulation of the particle. And since the liquid crystal has higher refractive index than the colloid, the particles cannot be trapped in liquid crystals. Okay, so the trapping mechanism here is very different, but essentially the point I am trying to make here is that you can use the focused laser beam to manipulate the particle in the sample wherever you want. So now look at some results. So this is a nematic phase of a liquid crystal, and I decrease the temperature. Okay, so you have a hyperbolic hedgehog defect here. Now I decrease the temperature and see what happens. Okay, so I am decreasing the temperature going from nematic to smectic-A phase. This is something strange in the sense that initially you had a hyperbolic hedgehog. Now in smectic phase you have a very strong, this bright color tells you that the smectic layers are strongly distorted around that region. Okay, and you have a dark line. This dark line can be even seen even if you remove the polarizers. Okay, so we ask the question, what are those actually?
So
Yeah.
what is the temperature which you will be?
Temperature range?
Yeah, okay, so that's not.
Yeah, this is around maybe 3 to 4 degrees, just above the to below the transition. Okay, this is a video across the phase transitions. Okay. Yes, it is weakly first order. It is weakly first order. Yes, you can. In fact, nematic to smectic is weakly first order, so it is difficult to answer your question. You will get superheating. You will get because it's weakly first order, but this is so small, hysteresis probably difficult to measure. Whereas nematic to isotropic, it has a large hysteresis because it's strong first order. You can actually measure. You can see under microscope, but smectic nematic is difficult because it's very weakly first order.
So how do you know
In fact, nearly second order actually.
how do you know it's first?
Oh, they do the specific heat measurement across the transitions, and this is one of the very known sample which is studied for various reasons. So what I showed is that the defect is transformed. Okay, a point defect has transformed to a line defect. The question is, what is that line? So look at this p-transitional state before I go to smectic. So what I see is that near this transition, when I go close to transition from that to this state, I have a strong distortion of this. The bright colors tells you that the layers, they deviate from the x direction. Okay, and therefore you get a birefringent color around this. And we know that actually when you have a phase transitions from nematic to smectic-A, the relevant elastic constants are K11 and K33, though there are 3, but 2 are important here, this play and bend elastic constant. You can see that bend elastic constant shows kind of p-transitional divergence as you approach to this smectic-A, which means layer structure, you cannot have a bend deformation of the molecules when you have smectic layers, because smectic expels bend. This is a kind of a superconductor type 2 analogy which was given by Huygens, okay, that magnetic field is expelled from the type 2 superconductor. So now in fact it was shown by Huygens that the K33 goes somewhere the K330 plus chi to the power minus 1, and so chi is the reduced temperature. So you can see this is rapidly diverging. So we know that means when you are going here to there, since this is the elastic distortion, the elastic anisotropy K33 and ratio K33 by K11 is rapidly increasing, and this can be seen in the simulation. So what we can do actually, we use this Landau-Huygens Q tensor modeling. This is the free energy. This A, B, C is the free energy involving the bulk order parameter, which is a Qij tensor order parameter. L1, L2 are the relevant elastic constants, which are actually connected to K11 and K33. Okay, L1 and L3 is connected to K11 and K33, and this term imposes the boundary conditions. And if we minimize this, and this is typical simulation parameters, you see that, of course, you use 2 by 2 Jones matrix so that you can see the colorful image. So when the elastic constants K11 and K33 are equal, that means when you are very far from the transition, there it is what you see in this experiment. But when the bend elastic constant is increased 8 times, the point defects actually move towards the sphere. If you see carefully compared to the other picture, the point defect moves towards the sphere, right? So this kind of deformation is actually forming because of strong distortion of the layers, and the point defect tend to move. But then what happened to the line that which I showed? Still I am in the nematic phase, not gone to the smectic phase. Okay, the Q-tensor modeling is not. This cannot be used for smectic phase transition because this only involves this nematic phase. So there is no theory, which is a unified theory, which can take and show this transition theoretically from one phase to other. But this does not prevent us to understand what actually happens when we have smectic phase. There is a experimental technique by which we can confirm. We put a lambda plate. Lambda plate is basically a retardation plate which gives you 530 nanometer optical retardation. Okay? And when you put between two cross polarizers, this is a Michael-Levy chart. This chart tells me that if I have a lambda plate, okay, 45 degrees with respect to polarizer analyzer, and if I have no birefringence sample, I will get magenta color. The moment you have a birefringence, that means a distortion, this blue and yellow color tells me how molecules are oriented with respect to this direction. For example, if you compare this Michael-Levy chart, look at from this, initially you have this kind of defect, and left side you have upper side is the blue, that means the molecules are actually having clockwise rotation. And if you come to the smectic phase, for example, here, enter this side is kind of bluish and it's yellowish, means that in this region, so that means smectic layers are actually having this kind of molecular orientation. If that is the case, then you have a smectic focal lines around which you have an opposite tilt of the molecules. So this kind of construction of layer around this particle is possible using lambda plate. Okay. So we found is that the point defect which we had in the nematic phase is transformed to a smectic focal line. Now we looked at this the equilibrium separation. Basically we track this in center to center distance across the phase transition. What you see is that this interparticle separation suddenly decreases as a transition. But if you track and plot, you see that you have discontinuity at the transition. This is a nematic phase, a smectic phase. But important point here to note is that interparticle separation increases as you approach the phase transition. Then you have a discontinuity at the transition. This discontinuity is marking the discontinuity of the elastic constant of the two relevant phases. Because if you remember, nematic has the curvature elasticity K1, K2, K3, but smectic has a B, that is layer compression modulus. So interparticle separation increases, there is a discontinuous jump by the transition, again the smectic-A phase increases. Question is, how do we understand such behavior of the interparticle separation across the phase transition? So while we are doing the experiment, we came across a paper which actually kind of Landau-Digen's Q-tensor modeling. They predicted how interparticle separation should depend on the elastic anisotropy. In fact, under strong anchoring condition, they predicted that d by r naught, where d is the interparticle separation, r naught is the radius of the colloid, should depend upon the elastic anisotropy, that is 1 minus k11 by k33 with a slope 0.087. We thought this is the system where we know the relevant elastic constant in the nematic phase. Okay, all numbers k1, k3 we know. So we took that number and we plot the elastic anisotropy versus d by r naught. You can see it's 0.24, 2.4 is around 2.43 of course, but then the slope is around 0.07, which is somewhat close to this what theory predicted. Okay, so this is some kind of a experimental proof about this prediction on the equilibrium separation between two embedded particles in nematic. So that means interparticle separation is increasing due to the increase in the elastic anisotropy, and I have shown you already that K33 really shows pretangential divergence actually, right? Now we took another kind of liquid crystals where this anisotropy is actually negative. Even then also we see that the slope is around 0.089, which is close to the experiment. So to check the generality that it is a general case, we change the particle size 5.28 micron, different types of liquid crystal. Essentially, we get that on an average slope is around. Yes.
Your anisotropic increases as you approach the phase transition.
Yes.
Individual electric constants will go down.
No, K33 increases much rapidly than K11.
Both of them increase.
K1 increases very slowly, very slowly. If you look at this, the elastic constant near the transition, especially, see this is happening near the transition. In fact, K33 shows some kind of reduced temperature to the power -1. Okay. So the point is that you essentially on an average you get elastic constant the slope of the that term. So that is 0.087. So that means we know this sort of understand why the interparticle separation increases as you go to the nematic phase. But now the question is smectic. Why again smectic-A phase? They tend to increase, and if you look at carefully, it seems some kind of a critical behavior across the transitions, right? This interparticle separation is, that means if you approach from smectic to nematic, it shows some kind of critical behavior. So then we just looked at that with reduced temperature, if you, the interparticle separation, if you plot with reduced temperature, and then you get some kind of exponent alpha, which is 0.38. And we repeated this for both the liquid crystals, different particle sizes, and we see it's around 0.38 to 0.36 like that. But then what is this? Weekly first order phase transition, yes.
And we have spherical exponents.
Yes. Yes. Okay. Now the question is, see, I have said only interparticle separation shows a critical exponent, but physically I have no understanding what is that critical exponent, from where it is coming, or the simple question is why the interparticle separation actually increases again in the smectic-A phase. Okay. I have no yet understanding. From here we see that alpha shows some kind of critical behavior with the critical exponent 0.38. But then we can actually soon link to this something which is already known. The B, the layer compression modulus of smectic,